level of technical details and scope of details in tools that were covered in the hands-on training workshops across a number of the themes that are relevant for national communications and biennial update reports, specifically for inventories, mitigation, vulnerability and adaptation, and support. And this webinar is the third webinar in a series organized by the CGE, and we're organizing this jointly with Winrock this morning, and it's focusing on the Monte Carlo approach to uncertainty analysis in the forestry and GHG accounting areas. So during this 45-minute webinar, we're hoping that you'll get a better understanding of what the Monte Carlo simulation approach is, learn the steps to carry out emission estimates and uncertainty analysis using the Monte Carlo approach, and have an opportunity to discuss that approach to emissions estimates and uncertainty analysis with experts who are going to be speaking shortly. And again, we have scheduled about 45 minutes for the presentation, and then we have an additional 15 minutes if we need that extra time. So our expert and presenter today is Ms. Anna McMurray, and she's an ecosystem services analyst at Winrock International, and she supported the development of REDD+ reference emission levels and forest reference levels in several countries, including Guatemala and Nepal, where she also applied the Monte Carlo method to estimate the uncertainty of the emission estimates. So in addition, for the discussion section, in addition to Anna, we also have Dr. Timothy Pearson joining us, and he is the Technical Director of the Ecosystem Services Unit at Winrock International. Dr. Pearson has developed standards and methodologies for carbon accounting in the land use, agriculture, and forestry sectors worldwide, and has written guidebooks and source books for carbon accounting. So after Anna's presentation, you'll have the opportunity to ask both speakers any questions that you may have. So I hope that's clear. And before we begin, just want to ask everybody before we start to mute your mic or mute your phone lines. And then for the Q&A session, after the two speakers have finished the presentations, do send your questions through the chat feature. And I think there's a link that's been made available to you for connecting to the session, so you should see that. And we'll try to accommodate as many questions as possible within the time that we have. And don't wait to the webinar if a question comes up as we're walking through the information. Definitely send those questions in, and we'll queue them up. So with that, I'm going to turn it over to the experts. Anna, the floor is yours.
Thank you so much, Mosumi and Baba, and thank you everybody who is participating in this webinar. So as Mosumi mentioned, I am going to be discussing this guidance document we developed on how to apply the Monte Carlo approach to uncertainty analyses in forestry and greenhouse gas accounting. To give you a really quick context, this guidance document was developed as part of a project funded by the International Climate Initiative of the German government. In this project, we were supporting the government of Colombia in implementing their national REDD+ strategy. Okay, so most of me already went through the goals of the presentation, but I really hope by the end that all the participants have a good understanding of what the Monte Carlo approach is, the basic steps to carry out the approach, and to understand some of the implications. And very quickly, what is Winrock International? Who are we? We are a mission-driven nonprofit business that works throughout the world. We focus on providing technical and project management services to implement projects worldwide. And our focus is really on science-based approaches to develop tools, build capacity, methodologies, and develop technical guidance like this guidance for the Monte Carlo approach for broad audiences. Okay, so about the guidance document, it really builds on the 2006 IPCC guidelines for national greenhouse gas inventories, in particular the chapter on uncertainties. As probably many of you are familiar with, this chapter discusses the Monte Carlo approach. However, it really doesn't go into the details, the nuts and bolts on how to conduct the approach. So that's really what we're hoping to do in this guidance document, give the details on how to conduct this approach. We are assuming that the audience does have a basic understanding of descriptive statistics and some experience in the application of basic statistics, for example, in applying the propagation of error method to calculate uncertainty, which we'll discuss in a few slides. Also, we discuss confidence intervals quite a bit, so the audience should be fairly familiar with that concept. So as I mentioned at the very beginning, this guidance document was developed as part of a project to help Columbia implement its RED Plus program, and therefore the examples are really focused on the forestry sector. That being said, I do want to emphasize that it is applicable to other sectors as well in estimating uncertainty in greenhouse gas accounting. And we do try to provide examples of different software that one could use to conduct the different steps of the Monte Carlo approach. We focus on Excel-based software. However, if the audience is comfortable using statistical software like R or SAS, that's always preferable. Okay, so a quick rundown of what are uncertainty analyses. There's 3 fundamental steps. First, of course, is identifying the sources of uncertainty in your emissions estimates. And you want to quantify these different sources of uncertainty whenever possible. And finally, the step we're focusing on today is combining the different uncertainties to come up with one final uncertainty value. And the IPCC guidelines provide 2 approaches to do this combination. The first approach is propagation of error. In this approach, basically, you take your uncertainty quantities for each data input and put them into a very simple equation, which in turn produces a final uncertainty number. And the second approach is the Monte Carlo simulations, which we will be talking a lot about today. So what are the conditions for applying propagation of error versus Monte Carlo? These conditions are discussed in the IPCC guidelines, but I do want to emphasize them today. So it's tempting to stick with the propagation of error approach to calculate uncertainty because it's very simple to go through this process. However, there's a trade-off to its simplicity, and that's it has very strict conditions for its use. The uncertainty of your data inputs needs to be small. The distributions of your data should be normal. You should be using simple equations. There should be no correlations between your data inputs. And there should be the same uncertainty level for different years of the inventory. On the other hand, Monte Carlo, which is considered more complex, has much more flexible conditions for its use. It doesn't matter the size of the uncertainty. You can use it for any distribution type. It doesn't matter how complex the equations you're using are. It doesn't matter if the data is correlated, and uncertainties can vary between different years. So obviously these are much more flexible conditions. Okay, before we go into defining the Monte Carlo approach, there is a key concept that everybody needs to understand, and that is the concept of probability density functions. And I'm going to be referring to them sometimes as PDFs, so just keep that in mind. Basically, probability density functions explain the range of values that a particular variable could have, for example, the value of an emission factor, as well as the likelihood that the different values of that variable represent the true value that we're looking for. So in this example, we have a normal probability density function. It has that famous bell curve to it, but there are many others. So in order to do Monte Carlo simulations, the analyst needs to identify PDFs that fit well with the distribution of the input data. Okay, and some, really quick examples of different PDFs that are available. The IPCC guidelines provide some examples: uniform, triangle, log normal, obviously normal, fractile, but there are many, many other PDFs out there. Okay, so the Monte Carlo approach, what is it? So it is basically the repeated generation of random values within the probability density functions of the input data. So in this example here, we have 3 data inputs. All of them have different distributions. And so we run simulations, and you can see the resulting simulations in these 3 graphs. And then once we have these simulations, we apply them to the model that we're going to use to come up with our final estimate. So when we apply these simulations, it produces a final distribution. And from that distribution, we can identify the estimate using the measure of central tendency, whether it's the arithmetic mean or the median, and then come up with the confidence interval of that estimate. Okay, so the steps to carry out the Monte Carlo approach. There are 5 basic steps. First, you fit the probability density functions to the input data. Then you run the simulations, combine the Monte Carlo simulations to come up with your final distribution. Based on that distribution, you calculate confidence intervals and then calculate your final percent uncertainty. Okay, so the first step is, in my opinion, the most important step, and that is fitting distributions of input data to probability density functions. So what you need to do in this step is identify the PDFs that have a good fit with the different data distributions. From my observations, a lot of people, when they conduct Monte Carlo uncertainty analyses, they kind of skirt over this step and just assume that the data has a normal distribution, when in many cases it doesn't, and that's going to affect the entire analysis and lead to inaccurate results. So how do you do this? How do you identify PDFs that have a good fit with the data? There's this will depend on whether the original data set is available. If it is available, which is obviously preferable, you should perform goodness of fit tests. And these are basically statistical tests that allow you that will show you how well different models or probability density functions fit with the actual observed set of data. There are different software that will do these goodness of fit tests for you. Software that we have used is our EasyFit and ExcelStat. Just a quick comment about the software that we mentioned. We're not necessarily endorsing them, but they're just software that we have used personally that are potentially good resources for the audience as well. So in many cases, the original data set is unavailable. For example, if you're using IPCC default data or data from a scientific article where you only have one value. In these circumstances, you really have to rely on your understanding of the underlying data and the metrics that are available. So, for example, if we only have the mean and the standard error of the data, then we would assume that the probability density function is normal. Okay, so step 2, running the Monte Carlo simulations. So basically in this step, you are allowing the software that you select to apply algorithms that generate random values based on the PDF that you've selected for the data. Some important considerations in this step is the selection of the software that you're using to run the simulations. Once again, some examples of Excel-based software are ExcelStat and Symvoy that do this. Some considerations when selecting the software. There's many Monte Carlo software out there. Is the cost of the software. Unfortunately, all these examples we provide are proprietary, so they cost money. But other software, for example, R is free. but that brings me to the second consideration is ease of use. So R is free, but it does require a certain level of understanding of programming in R. Other considerations are relevancy to the topic. There's a lot of software that's specific to one subject, for example, financial risk assessment, and those are probably not appropriate to greenhouse gas accounting. Okay, another consideration is the number of simulations that you are going to run. Basically, you want a number that will produce stable distributions. So, for example, if you select 10,000 simulations, every time you run those simulations, it should produce roughly the same final distribution. A good rule of thumb is to use 10,000 simulations because in our experience, that generally does produce stable results. And finally, and this is a detail, but a very important detail, is you should consider truncating your Monte Carlo simulations. So, for example, if you've identified a probability density function that fits very well with the observed data, but when you run your Monte Carlo simulations, you notice that it's producing negative values, and you know that that variable is not negative. You would want to truncate your distribution so it would only include positive values. Okay, so you've run your Monte Carlo simulations, and now you need to combine them to in the model of interest. So I've provided a very simple example. You want to calculate total emissions. So you have your Monte Carlo simulated emission factor distribution, and you have your simulated activity data distribution. You combine those and you multiply those together, and you come up with your total emissions distribution. And once again, this can be conducted in the same software that you use to run the simulations in the first place. Okay, so steps 4 and 5, calculating confidence intervals and percent uncertainty. So we have our final distribution here of total emissions, and we use that final distribution to come up with an estimate of the total emissions. Now we need to identify the confidence interval of that estimate. So if that final distribution is normal, we would use the same approach to identify confidence intervals as we would in the propagation of error approach. One important point to note is that the sample size is the number of simulations. So 1,000 or 10,000 or whatever you decide. For non-normal distributions, there are different methods of identifying the confidence interval. One common method, which the IPCC guidelines actually talk about a little bit, is the method called bootstrapping, and I'll talk about that more in the next slide. And once we have our confidence interval, you want to identify your percent uncertainty. This is exactly the same as in the propagation of error approach, so we're not going to talk about it here because it's not specifically related to Monte Carlo. Okay, so bootstrapping to calculate confidence intervals. So we have our final distribution, our final simulated distribution calculated with the Monte Carlo approach. We've identified the measure of central tendency that we're going to use to estimate the variable. In this case, we're using the median. We need to identify what the confidence interval of that median is. So basically, we take this distribution and we resample it a certain number of times. In this case, we've resampled it 10,000 times. And for every resampling event, we are going to recalculate the median of the distribution. And this, in turn, produces a new distribution of medians. This is called the bootstrapped distribution of medians. And using this bootstrap distribution, we will then calculate the confidence interval. Once again, there's different ways to calculate the confidence interval of bootstrap distributions. I talked about a few of those in the guidance document, but the one I recommend is using the percentile approach. This will depend on what confidence interval you're using. For example, if you're using the 95% confidence interval, you would take the 2.5% value and the 75 percentile value and just take the difference of them to come up with your confidence interval. If it was the 90% confidence interval, obviously you would take the difference between the 5 percentile value and the 95 percentile value. And this bootstrapping technique can be performed in the Excel add-on Excel Stat. Okay, so those are the basic steps for conducting, for applying the Monte Carlo approach. Now, the title of the guidance document, as well as the title of this presentation, is Applying Monte Carlo to Estimate Emissions, Uncertainty Analyses. However, we are advocating that if you do apply Monte Carlo to uncertainty analyses, you should also be applying it to actually estimating your emissions estimates. If you read the IPCC guidelines, it only mentions Monte Carlo for uncertainty analyses. So this is something that we feel strongly about, and this is for two reasons. First, applying Monte Carlo to estimate final emissions does lead to more accurate estimates because we are taking into consideration both the range and shape of the different data inputs, rather than just applying one single estimate. Second, and this reason is probably more fundamental to why Monte Carlo should also be applied to emissions estimates. When you only apply it to uncertainty analyses, there are potential incongruencies between the confidence interval calculated through Monte Carlo and the final estimate not calculated through Monte Carlo. And you can see in this figure what could potentially happen. The value calculated without Monte Carlo actually falls out of the confidence interval calculated with Monte Carlo. So this is a significant issue. Okay, so going back to Monte Carlo just for uncertainty analyses. As we talked about in the beginning, Monte Carlo does allow for the estimation of uncertainty under much more flexible conditions. And in comparison to the propagation of error approach. It also, that being said, it produces generally pretty low uncertainty values. And the reason why is because we are generally using a high number of simulations, this will inevitably lead to small confidence intervals. So it's good because these high number of simulations produce robust, stable results, but these robust, stable results lead to small confidence intervals. The implications of this is that, especially if you are only using Monte Carlo to estimate uncertainty and not actually estimate emissions, it may underestimate total uncertainty. Okay, so some final thoughts on the Monte Carlo approach. Because in many greenhouse gas accounting contexts there is large uncertainty, we are working with non-normal distributions, and many of the other contexts that require the use of Monte Carlo, it needs to become more common. We will produce more robust representative emissions estimates and come up with more accurate uncertainty results. There are two fundamental challenges to the wide-scale adoption of Monte Carlo, however. First is the lack of reasonably priced, thorough, and accessible software available to run the approach from start to finish. As you have seen, we tried to provide an example of Excel-based software that does this, but the only software that will allow you to go from step one, fitting PDF to the data, to the finish, calculating confidence intervals using Bootstrap is Excel stat. So there needs to be more software out there. There is also a lack of clarity, in our opinion, in the international guidance on how to apply Monte Carlo. So we tried to provide some more clarity, but the international community needs to clarify, for example, how to come up with confidence intervals based on Monte Carlo distributions. So those are my final thoughts. I tried to keep this under 20 minutes. I don't know if I was successful, but I think we can now open it up to Q&A. Thank you so much.
Good questions. Yeah, so hopefully everybody can still hear us. And so I'll just read out loud the first question for Anna and Tim. So the first question was, in step 1, which distribution would you use when it comes to combined values, such as for tree DBHs that are either in forest or non-forest? Individually, they may be normal, but their interaction may not be. That was our first question.
Right. So I think in that case, you really need to identify the PDF before you combine them, you should identify the PDFs of your input data to that combination. I don't have a clear answer. One would assume that the result would be a normal distribution just because it is a, I don't know, Tim, do you have any thoughts on this?
We would expect in a natural system like that probably to get a normal distribution. But regardless, I think the way you have to think about this whole Monte Carlo system is, instead of the way we traditionally have done, where we just linearly add up numbers, multiply, divide, with Monte Carlo, instead of those single numbers, we're just taking the full distribution, the full set of numbers that come into that, and putting together all these distributions in an additive manner until we finally get to the final distribution. So if there's any input number that has a potential distribution of numbers associated with it, then there should be a fitting of the shape of that distribution so that we can accurately model it and bring it all the way through to the end. It really is a different way of thinking about it and a much more accurate way of thinking about it, because we are including all the data instead of just continually taking the mean and taking the mean and taking the mean.
Yeah. I do just want to emphasize one point that Tim said. So let's say you don't have your input data and you just have one value of the tree DBHs. I think you would have to assume that it is a normal distribution because it is coming from a natural system. But that is only if you don't have access to the original data set.
Okay, thanks. So we have 2 more questions and maybe a few others coming in as well. So I'll just move on to the second question. And I think, again, just to flag that the slides are available, we'll be sharing information at the end about where you can get this information and have it for later for reference. So the second question was, is it still good to use Monte Carlo approach when we only have one emission factor value? The activity data are varied, or is it more applicable for analyses involving more than one value of both the emission factor and activity data?
I think it is applicable to both of those scenarios. It really depends on whether the input data you're looking at is normal or not. In the case when you only have one variable for emission factors, it depends on the shape of that distribution for emission factors. Now, going back to the slide on comparing propagation of error to Monte Carlo, propagation of error is better to use when you have simpler equations. So if you only have a few variables, it is safer to use propagation of error. So in the scenario where you have multiple variables, I would definitely apply Monte Carlo.
Okay. And the next question, and do continue to send your questions in. The third question was, do you have any documents or tutorials about the Monte Carlo approach? I'm assuming this is beyond the guidelines. And as most software that you need to buy, what is the most reliable software that we should choose? Excel is easier if available.
So I'm sorry, the first question,
do you have any, sure, do you have any documents or tutorials about the Monte Carlo approach?
So we do have the guidance document, which talks about each of these steps in a lot more detail. So I don't know, Baba, if you shared that on the CGE website, but I would highly recommend that the audience review that.
Yeah, Anna. Yeah, sorry, Anna, just to jump in. Yes, it's available on the CGE website, and then at the end we will share with them how to find it on our website as well.
Great. Yeah. So that is a step-by-step guidance document. So I think that should address the audience's question. So the second question, recommended software. This is an issue that, I identified in the last slide. As I mentioned, the only software that goes through the entire process is Excel Stat. When I've run Monte Carlo, I've used a combination of EasyFit to actually fit the distributions to different probability density functions, and then I've actually run the simulations in R. I haven't found any packages in R that will go through the entire process. I'm not familiar with the statistical packages like SPSS or SAS. I'm assuming they also have Monte Carlo functions in them, but this is a gap and a huge hurdle to implementing Monte Carlo on a wider scale.
I think that's some of the point that the Monte Carlo is really a fairly advanced statistical technique, and it's something that's fairly well accepted and used in some financial and gambling situations. And in those cases, it's there are approaches that are more developed. In this situation, it is not so commonly used. There will be more software being developed all the time. There will be some software that we're not aware of, but we're just trying to help in as much as we can, try and bridge that gap really between something that's an advanced statistical technique and the practitioner community who could really use this, because the limitations of the propagation of errors approach are fairly significant in a practical application like a greenhouse gas inventory, and therefore the only approach left is the Monte Carlo approach, and uncertainty is, as we all know, such an important part of any numerical exercise and in any reporting that comes out from inventories.
Mm-hmm.
Okay. Thanks. And so I think, Anna, related to your point, we have a follow-up question on R. So the question is, R is open source, but many of the participants have flagged we're not programming experts. Is there any ready-made R scripts or suggestions on using R?
No, there are no ready-made R scripts, at least from my research. And I spent a long time trying to find ready-made R scripts. What I would recommend, there are R packages that will allow you to fit distributions to different probability density functions. Unfortunately, you have to identify the probability density function ahead of time to run these tests, and that's very time consuming. And if you have no idea what potential PDFs could fit to the data, it's not that practical. So that's why once again, the software that I really love to do probability density functions is EasyFit, because it allows you to simultaneously run these goodness of fit tests on over 55 PDFs. But so going back to R packages, like I said, there's no R package that allows you to go through the whole process. However, there are basic functions in R, like the random number simulation functions, like R norm, R log norm, etc., that will allow you to run the Monte Carlo simulations. And then, so what I've done is use those functions and then applied the apply functions to incorporate the simulations into the equations to come up with final emissions. But that is, you know, I've had to jerry-rig that system myself. So unfortunately, I can't recommend any package that is if somebody is, you know, an R expert out there, that would be a great help to the entire international community to come up with this type of R package.
And we have another question sort of going back to the framework in the 2006 guidelines. Just to clarify, the Monte Carlo approach, should that be used for Tier 2? Is that correct? And so maybe it's a clarification in the methods, if you can address that, Anna.
Tim, I think that's probably a more appropriate question for you.
Yes, as I understand it, that propagation of errors is considered a Tier 1 approach, and Monte Carlo is the Tier 2 approach that's available currently.
Mm-hmm.
So I'm seeing if there are any other questions.
I think there was one more on if it is good to prioritize application to uncertainty per 2006 guidelines, and then consider implications for estimates.
I'm sorry, I'm not following that question. Can you repeat it one more time?
Okay. Is it good to prioritize application to uncertainty per 2006 guidelines and then consider applications for estimates?
I think you should always use the 2006 guidelines, regardless of. I mean, I don't know what other alternatives there would be.
I think, Anna, this is getting at the question of whether you're using the Monte Carlo approach to estimate emissions, even though the guidelines don't seem to that approach.
Yeah. I don't know, Tim. What do you think?
I mean, it is tough in cases where you have to conform with these guidelines when the guidelines have been done in this very siloed method, where there's the silo that looks at uncertainty, and then there are silos that look at accounting different aspects of the land-based inventory, while in reality you're applying a Monte Carlo approach. That suddenly is your accounting approach. And instead of adding different aspects of your inventory together by adding means, you're going to be adding those distributions, and you're taking a Monte Carlo approach. So if you're going to do it correctly, you're going to be embracing Monte Carlo and doing it fully. That's not to say if you're conforming with a standard that is going to be audited and verified, sometimes you don't have the choice to do it absolutely perfectly because you have to conform with the requirements. But the correct way to do it is to take a Monte Carlo-based approach to inventory, if that's what you're going to embrace at this time.
I do want to say, though, there's nothing in those 2006 guidelines that say you shouldn't use Monte Carlo to estimate emissions. You just need to be pretty explicit in writing up your methodology that you've used Monte Carlo for both emissions estimates and uncertainty.
Okay, thanks. I'm just seeing if there are any more questions, and I think that's an important clarification that if you do have a country-specific approach, I think that's consistent with the 2006 guidelines. But I will just see if there's any more. It doesn't look like there are any more questions. And Baba, I don't think there are any. So I may turn it over to you to wrap up.
All right. Okay, sure. Osmi, thank you. Thank you, Anna and Tim, for the presentation. People have been asking also if the presentation would be made available. And I just want to actually share our website on where this presentation would be available. So there's a couple of ways to reach this presentation through the UNFCCC website. So you have to go to unfccc.int. One option is to do a search, and you go on our main page, and here's the search function. And if you put in CGE webinar series, you will see it as the first hit that the search will give you. And under the CGE webinar series, you'll reach this page where you'll be able to see what were our past and what we are planning. And as you can see, we have already uploaded the presentation from today. It is here. We've also done a recording of this, so we hope to post that soon as well. So we will send out an email to all the registered participants of the webinar video once it's available. And then you can also see what we have programmed for the rest of the year. So there's a number of webinars that are being programmed for the rest of the year. I want to also show you one more way to reach all the work that we are doing on transparency and reporting. If you go to our main page and then go to process and meetings, you will come to transparency and reporting right here. And then if you go to reporting and review under the convention, then you will come across these various points. And if you go to support for developing countries, you will see the CGE link right here, and it should lead you to the main CGE page from where you can access all the information. It's a little bit slow at times, especially this time in the afternoon, but you will be able to access it. And also, if you would like to stay in touch on the work that we are doing, if you're on Facebook, we also have a Facebook page called the Mitigation and Transparency Exchange page, where we post information on the work we're doing, new publications, webinars, any other interesting information that has come out on this topic, so you can follow it there as well. So that is basically on our various outreach activities. So over to you again, Mosumi. Hi, Mosumi.
Oh, sorry, I was on.
So I'm done with my end. Back to you.
Okay, thanks. I just wanted to thank everybody for participating this morning, and hope this was helpful. And I guess we hope to see you in future webinars from the CGE, and look for future announcements. And I want to also thank Anna and Jen for providing this overview on uncertainty, which often and breaking it down a little bit, so it's helping others think about it, because it can be an intimidating topic for many. So thanks. Am I missing anything else, Baba?
No, that's it. Just that there will be an evaluation survey that will pop up when participants close the webinar. So please fill it out. It should only take you 5 minutes. It helps us to continue to improve our webinars that we are preparing. All right. Thank you very much.
Thank you.
Thank you.
All right.